All right, today we're diving into something that honestly feels like it's pulled straight from the pages of science fiction. We're talking about a totally new kind of computer chip, one that isn't programmed with code, but with an actual beam of light. Yeah, you heard that right. We're going to explore how we can literally sculpt circuits on the fly, and how it might just change everything we know about the future of AI.
So we all love what these huge AI models can do, right? But there's a pretty big problem brewing behind the scenes. The massive models that power everything from our chatbots to those incredible image generators are getting unbelievably thirsty for energy. The research is clear. As these models get exponentially bigger, their energy costs are also going through the roof. This isn't just a small issue, it's becoming a very real wall, a hard limit on how powerful AI can actually become.
So to get around this energy crisis, scientists have been looking at a really radical alternative: photonics. Instead of using electricity, using light, photons, to do the computing. The big dream here is that these optical computers could be way, way more energy efficient. But, well, the first attempts kind of hit a wall.
You see, the early photonic chips were built almost like Legos. They used all these separate individual parts that had to be physically wired together. This old method was just bulky, it was inefficient, and it created this messy tangle of connections inside the chip. But the real killer was the scaling problem. As the complexity of the AI model, let's call that n, went up, the area of the chip had to grow by n squared. That kind of scaling is just terrible. It meant they could never get big enough to be truly useful for modern AI. But what if you could just throw that whole box of Legos out the window? Instead of building a circuit piece by painful piece, imagine if the entire chip was just one single, continuous, and completely rewritable canvas. Well, that's exactly what this new breakthrough is all about.
So here's the core idea, and it is brilliant. You take a projector, yeah, pretty much like one you'd use for a presentation, and you shine a very specific pattern of light onto a special kind of chip. And that pattern of light doesn't just control the circuit, it becomes the circuit. You are literally drawing a computer into existence with a beam of light. It's wild.
The secret sauce that makes all this possible is something called a 2D programmable waveguide. It's basically a thin slab of a crystal called lithium niobate. And this crystal has this amazing property. You can change the way it bends light, its refractive index, just by applying an electric field. And in this setup, that field is controlled by light itself. It's the ultimate blank slate for building an optical computer.
Okay, so how do you actually paint this circuit? It's a really clever process. First, that projector shines its pattern, its stencil, onto the chip. Then, a special photoconductive layer on the chip reacts, but only where the light hits it. This reaction creates a super precise electric field inside the chip, which changes its properties exactly where you want, and that creates the perfect pathway for a second beam of light, the one that's actually carrying the data, to follow.
And listen to how one of the study's co-lead authors, Martin Stein, put it. He said, "We can essentially paint any optical circuitry we want, and then redraw it in the blink of a second." I mean, just let that sink in for a second. A completely reconfigurable computer that you can redraw almost instantly. This isn't just about making things more efficient. It's about making them adaptable, creating custom-built hardware for any problem, right on the spot.
Now, an idea this revolutionary, it really needs some proof, right? So to show that their light-painted computer wasn't just a cool theory, the research team gave it a classic AI challenge, recognizing handwritten numbers from the famous MINST dataset.
So the process kicks off with the input. The team takes an image, like this handwritten number 4, and they encode all of its pixel data into a beam of light. This beam, now carrying all that information about the 4, gets sent right into that programmable chip.
And as that beam of light travels through the sculpted crystal, its path gets bent and shaped by the circuit that was painted onto it. What's happening here is a physical process that perfectly mimics the math of a neural network. And when the light comes out the other side, the circuit is designed to focus it into one of 10 little answer bins, each one representing a digit from 0 to 9. Whichever bin gets the most light, well, that's the chip's final answer.
So what was the result? The chip nailed it, with an impressive 86% accuracy on the test data. Now, a digital computer can score a bit higher, sure, but that's not the point. This result is a massive proof of concept. It shows without a doubt that you can perform a really complex AI task just by passing light through a programmable crystal.
That 86% accuracy is awesome. It's a fantastic proof that this works. But believe it or not, that's not the main reason this technology is such a potential game changer. The real payoff, the
The reason this could totally revolutionize AI hardware is all about how it scales.
So what really makes this a true game changer?
It's because this chip doesn't just scale bigger, it scales smarter, and that is a fundamental leap in efficiency. Okay, here's the crucial part. Remember those old chips where the area grew as n squared with complexity? Well, this new design blows that away. Its area only needs to grow as n to the power of 1.5. Now that might not sound like a huge difference, but trust me, when the complexity of your AI model gets into the thousands or millions, the savings in physical space and energy are absolutely astronomical. This is the scaling advantage that could finally unlock that next level of AI.
So what this breakthrough really means is we're moving from just wiring computers together to actually sculpting them out of pure light. It opens up an entirely new way of thinking about the hardware that's going to power the next generation of artificial intelligence. The question isn't just, can we do this anymore? The question is, now that we can, what should we build next?